Hello everyone, I'm Zhou Zhen. Today I'm excited to discuss quantum optimization algorithms, a fascinating area of quantum computing. These algorithms have the potential to solve complex optimization problems more efficiently than classical methods. Optimization problems are about finding the best solution, such as the shortest path or the maximum value within certain constraints. Quantum computers, with the ability to leverage quantum phenomena like superposition and entanglement, could be incredibly powerful in solving these problems. We focus on two specific quantum algorithms in this presentation. First, the variational quantum eigensolver, or VQE, and second, the quantum approximate optimization algorithm, also known as QAOA. Both of these algorithms are used to solve optimization problems. Let's get started. Here's the contents of the presentation. At first glance, you might encounter many new concepts and unfamiliar terms, but there's no need for concern. In the overview section, I'll provide a succinct introduction to the structure and flow of our discussion. And as we progress further into the presentation, each concept will be unraveled and explored in depth. Before we get into the algorithms themselves, we need to cover some background knowledge first. We'll start by reviewing a couple of key concepts from quantum mechanics, Hamiltonians, and how quantum states evolve over time. Again, don't worry if these terms don't ring a bell right away. I'll explain them in detail. But having a solid grasp of this foundational stuff is really important for understanding how the optimization algorithms work under the hood. After that background section, we'll delve into talking about a specific class of optimization problems called quadratic unconstrained binary optimization problems, or QUBOs for short. These are the types of problems we want to be able to solve efficiently with quantum algorithms. We'll see how these QUBO problems can actually be framed or mapped into what's called the ground state problem in quantum physics. Then we'll get into the first algorithm, which is VQE. VQE is a clever way to find approximate solutions to the ground state problem by leveraging quantum computers. We'll go through the key steps and ideas behind how VQE works. Finally, the highlight of the talk will be the quantum approximate optimization algorithm, QAOA. This algorithm is motivated by a really fascinating concept from quantum computing called adiabatic quantum computation. So we'll first talk about what adiabatic quantum computation is and its relation to optimization problems. Then we will learn how QAOA itself works and see that it can actually be viewed as a specific instance of the broader VQE approach we covered earlier. By the end of this, you will have a solid understanding of not just how these quantum optimization algorithms works, but also why they are so powerful and exciting for solving complex optimization tasks, way beyond what classical computers can handle. So get ready for a deep dive. Let's start by visiting the concept of Hamiltonians in quantum mechanics. As the slide states, Hamiltonians are just observables that describe the total energy of a quantum system. The Hamiltonian is represented by an operator or matrix. Its eigenvalues correspond to the allowed energy values or state or levels that the system can have. And the associated eigenvectors represent the quantum states at each of those energy levels. This relationship is summarized by the equation H psi I equals EI psi I, where H is the Hamiltonian operator, psi I is an eigenvector or state, and EI is the corresponding energy eigenvalue. Essentially, the Hamiltonian governs how a quantum system will evolve over time based on its allowed energy and states, which makes understanding Hamiltonians crucial for the optimization techniques we'll cover later. Moving on to how those quantum states actually evolve over time according to the law of quantum mechanics. We have the famous Schrödinger equation relating the Hamiltonian h of t to the time derivative of the state vector psi of t. For time-independent Hamiltonians, we can solve this to get this equation. And u of t is called the unitary time evolution operator. For time-dependent Hamiltonians, the solution involves this product formula approximation shown on the slide. We split up the time evolution into n small time steps of size t divided by n, and approximate it as a product of small unitary operations. Now this exponential of a matrix looks complicated, but it actually comes from the power series expansion. So the exponential of A is just the infinite sum of the matrix A raised to successive powers with coefficients. However, an important point is that this infinite series only holds if A is a single matrix. In general, the exponential of A plus B does not equal to the product of exponential of A and the exponential of B unless the matrices A and B commute. Note that unless the matrices commute, we cannot simply split the exponential of a sum of matrices A and B into the product of the individual exponentials. This non-commuting property of matrices is very relevant when we derive techniques like QAOA later that involve splitting up the time evolution operator into a product of different Hamiltonian terms. Now that we have covered the essential background concepts from quantum mechanics, we can dive into discussing the specific class of optimization problems that quantum algorithms aim to tackle efficiently. The quadratic unconstrained binary optimization problems, or QUBOs for short. A QUBO problem is defined by trying to minimize a particular objective or cost function of this form, subject to x being a binary vector, meaning x is a vector of n binary variables that can take values 0 or 1. Q is an n by n matrix, and mu is another vector of length n. The goal is to find the specific binary string x that minimizes this quadratic function parameterized by the matrix Q and vector mu. Although it looks simple in expression, but it's incredibly difficult to solve optimally for large values of n due to the exponential size of the search space. These seemingly simple QUBO problems can actually encode a wide range of famous NP-complete problems that are incredibly challenging for classical computers as the size increases. Some examples include the max cut problem in graph theory, where we want to partition the nodes to maximize the sum of the weights of crossed edges. The notoriously difficult traveling salesman problem of finding the shortest route visiting all cities. Examples also include various scheduling and routing optimization tasks, and other important combinatorial optimization problems across fields like machine learning, network design, and beyond. Let's walk through a concrete example to see how a QUBO is formulated for the weighted max cut problem. The max cut problem asks us to divide the vertices of a graph into two distinct groups such that the number of edges between the groups is maximized. When we assign weights to these edges, the problem becomes even more interesting, as we now aim to maximize the sum of the weights of the edges cut by the partition. In this example, the graph contains 5 vertices and several edges, and the weights of the edges are different. We can represent the solution by a bit string. In this figure, node 1, 0, 3 are colored gray, and node 2 and 4 are colored purple. We can use the bit string 00101 to represent such partition. Of course, it's equivalent to use 11010. We can turn the problem into maximizing the cost function of this form, where W encodes the weights of all the edges. As you can see, even for this relatively small 5-node graph example, the cost function c of x involves many cross terms between the different binary variables xi, making it highly non-trivial to minimize. In fact, we can rewrite this cost function c of x in the standard Kubo form by defining the matrix Q and the vector mu in this way. Then we have c of x exactly matching the Kubo template. For this instance, the optimal cut represented by x equals 00101 or its complement 11010 achieves the minimum cost. In summary, being able to efficiently solve Kubo problems would be extremely powerful with immense applications, which is why there's so much interest in leveraging quantum computing for these tasks. Kubos represent a wide class of optimization problems where quantum algorithms may eventually achieve quantum supremacy over classical approaches. Now that we understand what Kubo problems are and why they represent an important class of optimization tasks, the next critical question is, how can we actually go about solving these Kubo problems efficiently on quantum computers? The approach is to map or encode the Kubo problem into what is known as the ground state problem in quantum physics and quantum computing. Essentially, we need to find the Hamiltonian operator Hc such that this condition is satisfied, where c of x is the cost function we want to minimize for the original Kubo problem, and cat x represents the computational basis states corresponding to the binary strings x. If we can construct such a Hamiltonian Hc that encodes the cost function Cx into its eigen equation, then minimizing c of x becomes equivalent to finding the ground state or lowest energy eigenstate of the quantum system described by Hc. But how can we actually build this mapping? Recall that the cost function of Kubos had this quadratic form, where x is the binary vector and q and mu are the parameters defining the problem instance. Then we can construct the corresponding Hamiltonian Hc as the following, where Zj is the poly Z operator acting on the jth qubit, and I is the identity operator. This complicated-looking Hc has a very special property. Its eigenvalues corresponding exactly to the possible values that the original cost function c of x can take over the binary strings x. Let me illustrate with a simple 2-qubit example. We can see that for this toy Kubo, the resulting H C matrix has eigenvalues 0, 0, -3, -5, which match the values C of x can take for x equals 0, 0, 0, 1, 1, 0, or 1, 1. So this equation holds for all possible binary strings x. You can pause the video for a while to verify the calculation yourself. So in summary, by cleverly encoding our original QUBO optimization problem into the ground state problem of a Hamiltonian operator HC, we can then try to leverage quantum algorithms to find this ground state, which will reveal the optimal solution x, minimizing the cost function C of x. Now that we've established how to map our original QUBO optimization problem to the task of finding the ground state of a Hamiltonian, the next crucial question is, how can we actually find this ground state on a real quantum computer? This is where the variational quantum eigensolver, or VQE algorithm, comes into play. VQE provides an elegant approach to obtaining approximate solutions to the ground state problem by leveraging the strengths of both quantum and classical computing resources. The core idea behind VQE is based on a fundamental concept in quantum mechanics called the variational principle. This principle states that for any Hermitian operator of matrix H whose smallest eigenvalue is lambda 0, and for any normalized state vector ket psi, this value will always be greater than or equal to lambda 0, with equality holding true only if ket psi happens to be the true ground state eigenvector of H. But why is this variational principle true? It comes from the fact that the term on the left-hand side of the inequality represents the expected value of measuring the observable H on the state ket psi, and the smallest possible expected value is precisely the smallest eigenvalue lambda 0 of H, achieved only for the ground state. However, there's one key problem. In general, we can't easily prepare or access arbitrary state vector ket psi on quantum hardware. The states we can create will be limited by the nature of the quantum circuits we can implement. This is where VQE's brilliant solution comes in. Instead of trying to prepare an arbitrary ket psi, we choose an parameterized quantum circuit, or ansatz, that can produce a family of states ket psi of theta as we vary its parameters theta. Here comes the algorithm. The overall goal of the VQE algorithm is to find the optimal parameter theta star that minimizes the expected energy with respect to the Hamiltonian H we care about. And it does this through an iterative process. The first step is to start with some initial guess for the parameter theta 0. The second step is to use a quantum computer to evaluate the expected energy. The third step is to use a classical optimization routine to update the parameters to a new theta that reduces the expected energy. Repeat steps 2 and 3, evaluating on a quantum computer and updating parameters classically until convergence. In the ideal case, this iterative algorithm will eventually converge to the optimal theta star, where ket psi theta star is the approximate ground state of H. Of course, there are many nuances like choosing a suitable ansatz circuit, developing efficient classical optimization routines, dealing with noise and decoherence, and more. But overall, VQE provides an elegant variational approach that allows us to leverage the strengths of quantum computers to estimate energy expectations, combined with classical optimization techniques. While the variational quantum eigensolver provides one powerful approach to finding ground state solutions, it is not clear how we should choose the ansatz. As it turns out, there is a fascinating quantum technique, which is called adiabatic annealing, that gives us inspiration on a way to design the ansatz. And as we will see later, this inspiration leads us to QAOA. Before we introduce adiabatic annealing, we talk about the adiabatic theorem that laid the foundation for adiabatic annealing. The adiabatic theorem from quantum mechanics states the following. If a quantum system starts in the ground state of some initial Hamiltonian, and the Hamiltonian is slowly varied over time, then the system will remain in the ground state provided that the change is sufficiently slow. This adiabatic principle has inspired a novel quantum computational paradigm called adiabatic quantum annealing, or adiabatic quantum computation for solving optimization problems. Here's how the adiabatic annealing method would work conceptually. We start with the simple reference Hamiltonian H0, whose ground state is known and easy to construct, like an equal superposition state. Then we encode our optimization problem into a final problem Hamiltonian HC, such that the ground state of HC corresponds to the optimal solution you want. Then we slowly interpolate or anneal the full Hamiltonian from the initial H0 to the final HC according to some schedule h of t, which is equal to a of t times h0 plus b of t times hc. If the annealing process is done slowly enough, obeying the adiabatic condition, then the system will ideally traverse the ground state at all times, ending at the ground state of hc, which solves the problem. A common choice is to use a linear annealing schedule like this, where Tf is the total annealing duration, and we smoothly interpolate between the initial and final Hamiltonians. The power of this adiabatic approach is that if done perfectly slowly, it allows us to find the ground state of extremely complex Hamiltonians, Hc, by leveraging a gradual path from a simple starting point H0. However, there are two key challenges with realizing this adiabatic computation. The first one is that if the system doesn't evolve slowly enough and violates the adiabatic condition, it can get stuck in excited states rather than following the true ground state all the way to the final HC. Even if the system remains in the ground state, finding the optimal annealing schedule or path for varying the Hamiltonian h of t over time can be extremely difficult for complex optimization problems. These obstacles have motivated researchers to explore alternative frameworks that can hopefully retain some of the power of adiabatic evolution while being more amenable to implementation on near-term quantum hardware. And this brings us to the brilliant approach behind the quantum approximate optimization algorithm, or QAOA. So the core idea behind QAOA is, instead of trying to implement a perfect analog adiabatic annealing schedule, we approximate this continuous adiabatic evolution using a cleverly designed discrete sequence of quantum operations or gates. Essentially, rather than having the optimal annealing schedule be specified upfront, QAOA aims to learn or optimize this sequence to mimic the adiabatic path as closely as possible. But how exactly can we approximate this continuous adiabatic process with a discrete sequence? To understand this, we need to recall a key result from the time evolution of quantum states. For a time-dependent Hamiltonian, h of t equals a of t times h0 plus b of t times hc, where h0 is the initial reference Hamiltonian and hc is the problem Hamiltonian we want to evolve to. The general solution is this, where u of t is the unitary time evolution operator given by this product formula limit. Now, using a technique called Characterization, we can approximate this infinite product form as the following, where we have divided the total time t into n small time steps of size delta t and approximated each short evolution by separating out the a and b coefficient terms for h0 and hc respectively. So in this characterized form, the full-time evolution u of t is approximated as a sequence of unitaries alternating between operators derived from h0 and hc, with some coefficients a of I delta t and b of I delta t at each time step I. And this is exactly the approximation that QAOA exploits. Instead of trying to directly specify these time-varying coefficients a of t and b of t, QAOA simply treats them as variational parameters to be optimized. Let's denote the parameters as gammas and betas. The QAOA state ansatz take this form, where cat psi 0 is some easy to prepare initial state, often the equal superposition. By carefully optimizing the parameters gammas and betas, QAOA can hopefully find a sequence that approximates the full adiabatic evolution and steers the system towards the ground state of the desired Hamiltonian HC, which encodes the solution to our optimization problem. This discrete approximation provides much more control compared to trying to implement an analog adiabatic annealing path. And as we'll see, QAOA can actually be derived from the variational principle similar to VQE. So in a sense, QAOA combines ideas from adiabatic evolution and the variational approach in a clever way amenable to implementation on gate-based quantum computers. This hybrid algorithm has shown very promising results for certain optimization tasks. After discussing the form of the QAOA ansatz, we now have the full picture of how the QAOA algorithm works. We just need to plug this ansatz into the framework of the VQE algorithm. For the parameters, we now have alternating sets of gammas and betas to optimize over. For the operator HM in the QAOA ansatz, we choose it such that its ground state is precisely the equal superposition state, which is obtained by applying Hadamard gates to the all zeros computational basis state. A common choice for HM is to take it as the negative sum of single qubit poly-X operators. By then, variationally optimization the gammas and betas, we steer this initial equal superposition towards the ground state of the cost Hamiltonian HC, which encodes the solution to our optimization problem. What a basic QAOA shows promise, researchers have proposed some interesting extensions. One approach is recursive QAOA, where you recursively run multiple rounds of QAOA, and at each stage, you reduce the number of decision variables by 1 according to the correlation data from the previous round. Another extension is Warm Start QAOA. Here, you first solve a relaxed version of the problem by dropping the discrete binary constraints to get a continuous solution. You then construct the initial state for QAOA according to this continuous warm-up solution, hopefully providing a closer starting point to the final discrete answer. These extensions aim to further improve QAOA's performance on difficult optimization instances. They're part of the ongoing research effort to enhance the core QAOA algorithm. Finally, let's take a look at QAOA's pros and cons. One of the key strengths of QAOA is that it is designed specifically for quantum processors in the noisy intermediate scale quantum era, also known as the NISQ era. This means it is tailored to work with the quantum computers we have today, which are noisy and have a limited number of qubits. This makes QAOA a practical choice for quantum optimization problems in the current landscape of quantum computing. However, one significant downside is the lack of performance guarantees. Unlike some classical algorithms, QAOA does not provide a guarantee on the quality of the solution. This means that while it may find a good solution, there's no guarantee that it will always find the best or even a near optimal solution. Another challenge with QAOA is the requirement for high circuit depth. In the case of QAOA, to get better solutions, we often need to increase the depth of the answer circuit. However, increasing the circuit depth can lead to more noise and errors in NISQ devices, which can negatively impact the quality of the solution. This is the end of the main presentation. Thank you all for your attention. However, with my decision to keep the core presentation flowing smoothly, I skipped over some of the detailed proofs or derivations behind certain concepts that you may find skeptical or want to see fleshed out further. Not to worry, in the next few supplementary slides, I'll walk through some mathematical illustrations and derivations for key ideas and results covered earlier. This will provide additional analytical justification for some of the claims made during the main presentation. Feel free to stay tuned for these more technical derivation slides if you're interested. But for those just wanting the high-level overview, this concludes the core quantum optimization presentation.